Hello, hello, hello. Can you guys to our annual distinguished speaker lecture, which was down in by Captain, where internet is conflicting ways to pronounce his name. And you might have read it already, that he was a baby crypto analyst in World War II and was credited in helping significantly with naval intelligence that led to victories in the battles of Midway and the Coral Sea. And then after the war, he was taken Navy, he had been providing security in person bomb tests in the Pacific. And then Navy decided to send him to school to learn nuclear physics, which he did from Ohio State. I don't know when.
That's what you said then, too.
And 2 years after getting master's degree, he retired and became professor at Cal State Long Beach. Also became around Caltech quite a bit, which is why we have this. So the memory of this past. Okay, so now it's my great pleasure to introduce our distinguished speaker, Juna Kollmeier from Carnegie Science. I've known Juna since she was, well, this all. She was, in my career, I probably advised about 80 or 90 undergraduate research students, mostly through a third program, and many of them went to distinguished careers. But one stood out, even back then, we knew that she's going to go high. There she is now. Don't worry, I won't mention the paper for this.
I know, I still owe it. I still feel bad about it.
Carnegie Princeton Fellowship, which I got somehow. In 2008, she joined staff of Carnegie Observatories. And I think in 2021, moved to Toronto to be director of the Canadian Center for Theoretical Astrophysics professor. In the meantime, she also became the leader, director of whatever I call it, the eye of the fifth generation Sloan Sky Survey. And now she's back to Carnegie.
Thank you so much, George. It is a pleasure to be here. I think when George says that I stood out, it was just like, who is this alien that is here? And is this human? Like, what is going on with this person? How do we teach this? Like, what? She doesn't seem very amenable to our instruction. She's not listening to us. Like, what happened in the admissions process? So I'm going to be talking about Spectra ex Machina, and of course, I came to Carnegie and started the Carnegie Theoretical Astrophysics Center. We started the theory program in 2008. Part of my how I get jobs is to say, you really need to do this, and you're not doing it, and you really should do this. And so I recognized when I was a postdoc at Carnegie that they had no theorists. I was the first theorist they had hired, and I was isolated. But I recognized that it was a real opportunity, and the opportunity was because you had all of this telescope time. And here was a place, there was not very many places in the astronomical world that didn't have a theory program, but had all of this observational data. And I had gone to Ohio State where I was trained as an observationally oriented theorist, but a lot of that started here at Caltech. So how I first got here, and I'm only going to reminisce for like a little bit because I have a lot of slides to go through. But I do want to reminisce a little bit. I was choosing between different schools for undergrad, and as a first generation college student, I didn't really have a lot of people to guide me. My research advisor had gone to Caltech, so that seemed like a good place to apply to. So, okay, I was from New York, didn't really know about Caltech. And it was John Schwartz and a conversation with John Schwartz where he said, well, you know, Caltech is really similar to all the other excellent graduate programs, but for undergrad, it's a really special place. And, you know, John had these like really bushy eyebrows. And like, I was like, okay, this guy is like a wizard telling me this information. This is like the right place. And then of course, I really loved the other undergrads, and I just had absolutely no idea what I was in for at all. And in fact, the final decision was made by the magic 8-ball. I just asked it, you know, if it was a good idea, said yes. So I don't recommend that, but I do recommend Caltech. And I wanted to do physics. And so I remember procrastinating my physics homework in the bridge reading room, which I went to and took a picture of the other day. And at that time, there were all the preprints around. And I sat down and I was looking at the preprints. Now there's just this CERN Courier magazine. So you can't really, in a conference table, so you can't really sit there with the preprints, I guess. But I looked at the preprints, and there's papers with like all these authors, like hundreds of authors. And I was like, how do you do that? How do you distinguish yourself in that whole world? Like, how does anyone know who anyone is? I can't even remember that many people. Like, how do you do these big collaborations? And I was like, okay, experimental particle physics. Like, I don't see how I fit in there. And so I figured, okay, this is not necessarily for me. But I knew that I wanted to stay in the physics track and the theory track. But George took pity on me. And one of the seniors in Blacker House, Vandana Desai, who is still here, and Roy Gal, you know, Vandana was an undergrad working in the DPOS Army, and she got me, you know, surf with George, and I was able to not just learn how these big surveys worked, but I was able to skip class and go to Palomar, which was awesome, because I never wanted to do class. I always wanted to do research, which is also a mistake. I don't recommend that. But this was a really transformative thing. And you could just go to the telescope and you could I wasn't one of these students who, you know, sat on, you know, made their own telescope as a kid and like looked up at the stars and wondered. Like, that wasn't the kind of student I was. I was a student that got into astronomy through, you know, through computers and through kind of thinking about different, you know, theoretical things. So this whole thing about the telescopes was new and exciting to me. But it was this class that I took junior year, AY 127, which was TA'd by Alice Shapley and Pat Udom-Pressert. And those of you remember, in 1998, Boomerang made a flight, and Professor Lang, Andrew Lang, who's a great physicist and also my Phys 2 professor, had figured out, Boomerang results figured out that the Earth, that the universe was flat. And flatness was really important if you were an AY 127 student, because you went from, Chuck was like, well, you don't have to do the numerical integrals and include lambda. Like, he was a really nice professor. But Alice and Pat were like, the universe is flat. Like, if you want the right answer, you have to do the integrals. And so they were fantastic. And it was just to say, a lot of my thinking about the world happened in that time, which is now a long time ago. But this map was similar to the sort of LIGO discovery. This totally changed cosmology. It totally changed everything. And I was like, I want to be a cosmologist for sure. I want to be a cosmologist. How do I become a cosmologist? And that's when I got engaged in the Lyman Alpha Forest, and through my senior thesis with Chuck, where I learned that I was not actually an observer. I was not a good observer. I do not have the patience and meticulousness and whatever to be a good observer. But I was like some weird hybrid thing. So that's all the reminiscing I'm going to do. Well, there's a little more, but in 2017, I was here and I was talking to you guys about SDSS-V. It was called AS4 then, after Sloan 4. And I concluded my colloquium with, we're currently in a phase transition. It's looking like we're going to do this. And there's a lot of skepticism, I think, in the audience. And again, it was the same thing where I just had no idea what I was getting into in any way. I had no idea what I was signing up for in terms of what we were building. I had no idea what I was signing up for. But there's a certain, there's a certain arrogance of ignorance that it kind of does propel you a surprisingly long way. But, TLDR, we did it. We did it. So, those of you who have, you can open your email, and I remember the commencement in 2000. And I say this, who is graduating or a student? Is there any graduating students in the room? No? Okay, sort of you. Yeah, you're tentatively raising your hand. Okay. This quote from Ray Bradbury from my graduation has served me so well in all the times where it was like, oh, I don't know if we can do this. I think this is going to be too hard. Can we really do this? Which was totally the theme of my undergraduate experience. He's like, call up anyone who said you couldn't do it and tell them to go to hell. And I really, if you haven't read Fahrenheit 451 lately, I highly encourage that. But I think this is really important because as I was talking with the graduate students today, one of the things that is so hard in navigating science is, what to do next. Can we actually accomplish that? Can we be audacious? We don't want to be so audacious as to not accomplish what we're setting out to, but we want to actually push the boundary. And so this quote I give to you as well. And I just said thank Caltech both for really shaping my brain in ways that I didn't quite appreciate, and for joining SDSS-V, of course, and for, Caltech was the first supporter of SDSS-V, and I have to credit Sri Kulkarni for that. The first person who donated to AS5 was Sri. And I'm really grateful. I'm grateful for the training I got here, and I'm grateful for your participation in SDSS-V. So SDSS really does live in this tension between discovery telescopes, which just get a lot of data. And if you get a lot of data, there's stuff in that data that is, astronomy is so phenomenologically rich. There's a lot of interesting things in that. Big experiments, so industrial experiments where we're getting, organizing things and doing a big project and having all of that as well. SDSS sort of lives in the mid space, and it's a mid-scale project. And I think that's one of the things I think is really fun. And SDSS has always been guided by theory testing. And most observational programs are, or many observational programs are guided by theory testing. That's certainly something that I took from Caltech. Of course, there's also discovery. So what we try to do is we try to have theory testing, but leave a lot of room for discovery. The original SDSS had a simple mission, which was to map 1 million galaxies. And of course, the SDSS telescope with the imaging and spectroscopic programs. You see these old fiber plug plates where a person had to plug a fiber plate, 1,000 times, 10 times a day. So it's a lot of plugging fiber. You can see what those look like in terms of how that maps onto galaxies and quasars. But this whole idea that we were going to do an experiment with a telescope and figure out the large scale structure sort of guided the original SDSS. And it was really, kind of going through this, in this, huge revolution of, well, we think that this structure is clumpy. How clumpy is it? What can we learn about the clumps in the substructure? And so going from the CFA Redshift survey to SDSS, not only did we get things like baryon acoustic oscillations, which is a whole new technique for learning about large scale structure, but also there was so much information in the galaxy spectra, so much information to learn about how galaxies formed, how they evolved. And it's super complementary to the things that happen on the big telescopes, which are really by nature much more detailed, much more focused, much more very complementary to these large statistical programs. Now, the cosmological register surveys have gone to larger aperture and in space, and congratulations to the SPHERE-X team and to the PFS team for those successes. So as the DESI survey has gone to the 4-meter class telescopes, and that we very much had a lot of the heritage from SDSS brought over to that program. What do you do with the smaller aperture telescopes? Is there still interesting things to do with those smaller telescopes? And I believe the answer is very much yes. And that answer lies in astrophysics. So these telescopes work really, really well, but you have to instrument them for doing really cool astrophysics. I like to think about old dead people a lot. I do that a lot. But 10x or die is something that you hear in many different circumstances. Where does it come from? Obviously, you have to do an order of magnitude leap in something in order to make a significant gain. And so I always thought, okay, this is like some Silicon Valley, let's 10x this, 10x engineer, 10x software. Like it's just some whatever internet blah, blah. But actually, no, it's Galileo. 10x or die, which is great. So Galileo writes in Sidereus Nuncius, and Galileo is arguably the first public data release, open science guy. The number of fixed stars which observers have been able to see without artificial powers of sight up to this day can be counted. It's decidedly a great feat to add their number and to set distinctly before the eyes of other stars in myriads, which have never been seen before and which surpass the old previously known stars in number more than 10 times. So that's where 10x or die comes from. So it's that's not really, but in my mind, that is where 10x or die comes from Galileo to us. And so that's what we have to do. So what is SDSS-V? So SDSS-V is, it's a science survey, and I'll go through each of the mappers. And of course, at the level of this colloquium, it'll be super general, which I feel super bad about. I would love to be giving you some super detailed calculation, some super cool new observation, but I'm going to have to give this broad overview. We are an observing facility, so we're telescopes, so we're instruments, we're people that operate those things. We're a consortium of partner institutions like Caltech, and of course, most importantly, we're a collaboration of humans. Bernie Fanarov said, of these mid-scale collaborations, they're as big as a project can be while remaining strictly scientific and rational. That's really important. A lot of times decisions have to be made politically, and that sucks. That's politics and science are not always aligned. And so it's really great to be leading a collaboration where we can still make those decisions rationally. This consortium is over 70 institutions spanning 5 continents, including many institutions in Chile. All of the CNTech institutions are members of SDSS-V. And I'm extremely proud of this international collaboration. Raise your hand if you weren't born in the United States. You don't have to raise your hand if you don't want to. Okay, so we collaborate. Science is international. Science is something that we can do across our very significant cultural divides, and I think that's a testament to it, and I'm proud of that. In terms of project organization, in every SDSS, there's a huge number of people who make it happen. And I remember, again, when I was youthful, the graduate students in the room, raise your hand if you're a graduate student. Yeah, so you guys, I would see a chart like this, and I'd be like, oh my God. Who would want to do anything associated with that? That looks horrible. Keep that thought. That's the right instinct. Okay. But actually, if you want to do a big thing, you got to work with a lot of people, or be Einstein. Either way. But there are a ton of people who we really actively cultivate to be the next generation leaders in not just in science, but in data analysis, in pipelines, in control and operation software, in all sorts of different areas. What I love about the SDSS project is how many places there are for you to contribute. So there's a lot of places for you to be an individual contributor and really make a difference. And there's also the opportunity to just be like, I'm just going to do my science. Like, I'm not going to be, in this whole kumbaya thing. And you can do that too. And I think it's really, really important that we have a lot of different mechanisms for people to work in astronomy. I think it cultivates the next generation. So now I'm going to go on to briefly describing all of our mappers. So we've got 3 mapper programs in SDSS. First is the Milky Way Mapper. And the real question that we're asking is the Milky Way simple structurally? And what is the structure and the order and multiplicity of stars in life and in death? And that's our Milky Way Mapper program. In our black hole mapper program, we're kind of asking the fundamental questions. What are the mass functions of supermassive black holes? And how do they get their mass? And for galaxies, we want to know how they actually work in the context of lambda CDM. Not plausibly so, but realistically so. And our way to do that is the local volume mapper. So the Milky Way Mapper first. The major thing that really changes the game, at least from my perspective, is being able to get stellar ages accurately across a broad range of ages. And this is super important because whatever any simulator tells you about their models, and Phil, there'll be many chances for you to argue with me, age is something that is just very naturally and robustly predicted. So the time when something happens, when stars form, when gas gets blown out, those things are robust things that we measure. It doesn't depend on some really complicated NLTE yields, like all sorts of deep theoretical modeling where there has to be a lot of tuning. It's actually really natural. So if we can get the ages across the Milky Way, we can dissect the Milky Way by age. And that's a really robust thing that we can say, that we can actually have to compare with calculations. We can say, when did the disk of the Milky Way or Milky Way-like galaxies, when are those things forming? Do we have really hot turbulent disks forming Milky Ways generically? And by making these age estimates, it really changes the game in terms of substructure and what we can compare. So that's something that motivated us in SDSS-V to really go after a lot of stars. So these are now age maps from Melissa Ness, who's one of our survey scientists, and Alex Martinez, who's a graduate student at New Mexico State, using different methods to measure age. You can see the young disk, and you can see the older, thicker population, but also there's substructure in there. And what does that look like? So there's a lot of opportunity. If you're a student, you're interested in, or a postdoc, and you're interested in digging into this, there's a lot of opportunity. This is only 400,000 stars. So we're going to have 4 million stars in this particular selection that you can actually really start to do galactic archaeology, not just by the abundances and the kinematics, but also by age. So I'm very excited about that. The extent of the Milky Way Mapper survey is much broader than Apogee. So this is the previous Apogee coverage, and in SDSS-V, we're going. Of course, we have the southern sky, and we're doing that much more detail. So in terms of the structure that we sample, it's much more, it's much broader. And we're going beyond just spectroscopy and the red giants. We're actually doing spectroscopy across the whole HR diagram. And so there'll be something like 6 million stars in the Milky Way and Magellanic Clouds with high fidelity abundances, with ages, with all the good things you need. Now, we may quibble about targeting, and Kareem gave me a hard time about some of the targets that we're doing this morning, but because we're a rational survey, if we're doing something that, if we're targeting the wrong things, we can change course and target something different. And I think that's something that I'm I'm happy about. So we're going to do 10x the number of apogee stars. And in terms of this binarity, in terms of stellar architectures, if you just take a solar mass primary and ask what sensitivity you have to a secondary, this is the separation that you're sensitive to, and this is the secondary mass. This is assuming our 30 meter a second radial velocity accuracy, which we know, thanks to Andrew Sagery's excellent work, we're getting. You're sensitive to all sorts of stellar system architectures, including some hot Jupiters, which is exciting, but also all of these other companions. And I am excited about this because we really want to understand the binarity across the HR diagram. We know binaries are very important for stellar evolution, and this is kind of low-hanging fruit in terms of measurements. Our black hole mapper. So, of course, the first solution to Einstein's field equations was the Schwarzschild solution, and it took a really long time. Think about how long it took for people to realize that the AGN were the black holes, that these were the same thing. And of course, these are the AGN spectra from SDSS-1 to 4. So black holes are weird and cool, and we love them. But actually, we've had this picture of sort of the phenomenology around AGN for a really, really long time. So whenever you see a diagram and it's got like clouds, like cartoon clouds and stuff, and PowerPoint arrows, like that's an opportunity. That's an opportunity for a student to like totally change the game. So when you're looking at it one way and it's the broadline region, and you're looking at another way and it's radio loud and radio quiet, and this way and that way. And our paper, which I've owed you for like 30 years, was about the flat spectrum radio sources, the obscured sources. I think it's still very interesting. But we want to understand how this accretion proceeds. So looking at not just measuring the black hole masses, which we're doing in our reverberation mapping program. So you're familiar, most of you, I'm assuming, with reverberation mapping, where you basically look at the response of the broadline region to changes in the continuum. That gives you a distance. You have a velocity. You can get mass from that. We're 10xing the sample of reverberation mapped masses in SDSS-V, but also we're looking at multi-epoch AGN spectra. And for those of you who are working in ZTF and in the surveys here, you are very, very familiar with these objects. We really want to modernize this picture of the circum-black hole environment. What does it really look like? And so the idea of targeting these things multiple times is so that we could actually get a handle on the different time scales and different length scales in the AGN. Of course, we're comparing. We also have ERA-zeta data at harder wavelengths in the X-rays. It's important to compare there. But I want to show you this. It's unpublished yet. This is from James Owen and Doug Lin, and this you're looking at temperature, density, and dust to gas ratio. And this is a failed dusty wind. So you just have you have dust that's getting kicked up out of the accretion disk. I'm only showing this to you not so that you can draw any quantitative conclusions, but just to show that actually this, the time scale, what you're looking at are dust blobs that are getting, kind of almost launching, but actually collapsing back down into the disk. You can see that if this is really what's happening in the AGN disk, that's going to have a very different picture of the broadline region than what we've typically had. And this is, then there's, explanations for why it actually matches black hole mass. So look out for that paper when it comes out. But what excited me about this when James showed it to me is that the time scales of all of these activities, the launching of the wind, the failure of it, and also the circulation within it, those time scales are imprinted in the spectra. And so in principle, if we had the sample that we've been collecting, which we kind of knew we were going to have, which is why we did the program, we can start to constrain these pictures. And I think that's super exciting. We're doing lots of black holes across the whole sky. So this is in our overview paper, but you can see these are all different types of targets, reverberation mapping targets, time varying targets. This is according to our current survey plan across the whole sky. So it's just a huge amount of data. This is the total kind of MOS target density across the sky. Not that that's just to show how we have all sky coverage. But importantly, overlaid in gray is our local volume mapper, which I'm going to talk about. And just to say, the thing that made this possible was going from plates to robots. So we replaced the focal plane of both of our telescopes from that plug plate technology with robotic fiber positioning system. We have, so we built 2 of them. Each focal plane has 500 robots, one going to optical spectrograph, one going to an infrared spectrograph. And that's how we're able to increase these numbers so substantially, because our survey speed is just tremendous. It's gone from months to our survey planning from months to minutes. So finally, our local volume mapper. So our local volume mapper is our most ambitious project within SDSS-V. And so this is really, Phil has been telling us for decades about how these galaxies are regulating themselves, right? And I think the real question is this true? And in what sense? And in which of these different models with these different sort of subgrid recipes, which is actually the truth? They all produce the luminosity function. They all make amazing pictures and all make amazing movies. But there are real differences in the physics that we care about, that we'd like to understand. And so where are we going to look at it? I think there are 2 places that you look at it. The one place that you look at it is the circumgalactic medium, and Chuck taught me that. And that's really hard. And the other place you look at it is in the interstellar medium, because that's where energy is actually being injected. So we're looking at galaxies at the energy injection scale with an IFU in the optical. So if you look at sort of previous surveys, they kind of had 100 parsecs per spaxel or maybe 50 parsecs per spaxel. If you look at something like FANGs, we're really going down to a pixel, a parsec per spaxel in the Milky Way, and in the Magellanic Clouds, 10 parsecs per spaxel. So that now is at the scale that the kind of calculations that Phil is doing can really be tested. So what does this look like? And we built a new IFU. It's what you see here is the moon. The IFU, 1,800 fibers in the focal plane. You can see it's about the size of the full moon, which is why we put it there. And we just tile the sky with this IFU, and it's feeding 3 DESI spectrographs. Or DESI-like spectrographs, they're slightly modified. This is the IFU map of Orion. This is the survey extent. So you can see we're doing huge swaths of the interstellar medium of the Milky Way. We're doing the Magellanic Clouds. We're also doing these little dots here are just a kind of blank kind of regular pattern survey without specific H2 regions or targets. All your favorite H2 regions are being covered. There's if you look at this is really at a data volume level that is bananas. So I really would love for more people to get excited about this and think about this, because the type of data set we have, we kind of 1,000x'd it, which is like a little too much. We're overwhelmed. So this is the full moon. This is the Rosette Nebula. That's what it looks like from an amateur. The pink picture is just a H alpha picture. That's what that H alpha looks like in the LVM. You can see there's 7 pointings of the local volume mapper. So what does this look like? And Tom Herbst makes these awesome animations. This is oxygen, hydrogen, and nitrogen in the rosette. So you can see what that looks like. But now, what are we going to do with this thing? So now you have all of these different lines of sulfur. Okay, you've got all of these different lines of oxygen, hydrogen, nitrogen. You got everything. The optical has a lot of stuff in it. You also have the X-rays, the diffuse emission from E Rosita, and radio. So like we've got the interstellar medium. It's done. So this is 19 tiles of the LVM. It's about 35,000 spectra in all of these different bands. This is just kind of what the spectra sort of look like. This is just different pieces of it. And now we're just going through and looking at what this data looks like at every one of these wavelengths. So the thing that, as a theorist, like when I look at this as a theorist, I'm like, well, that's like very complicated. What I want to see is rho T gamma. I want to see density, temperature, and ionization state from in the gas. And I think that's the thing that I can compare most robustly to the kinds of calculations that the simulators make. And I think we will get that with this data. And so that's very exciting. It just kind of shows what this looks like. Here's the velocity field and the velocity dispersion. There's a ton of interesting information in this data set. And this data set is massive. So if you think about, that's just the rosette. Like you all at Caltech have access to all of this data. You can go to the LVM visualization tool and like scroll through all of this data, comparing it with all the publicly available surveys. This is just a picture of the LMC and the SMC with the LVM. And so you can see the cool structures. You can see all the supernova remnants and new H2 regions. This is a really rich data set for discovery. Just in the final few minutes here, how it started is like, just a bunch of, people in the room. This is my Physics 1 TA, David Hogg, who is now the AC chair and is one of the sort of data science gurus in the world. That's us at our first kickoff meeting at Carnegie. It was really hard to build this thing during the pandemic. So when everyone's workshop closed and it was really challenging, and I really want to call out Stephanie Wachter and Solange Ramirez, our project manager and lead systems engineer, for their work here. Stephanie built a cardboard version of our focal plane system in her driveway to see that the routing was going to work. So building all this stuff in the pandemic presented like a unique challenge. We built a lot of stuff, and it's now all working. The IFU is working, the focal plane system is working. It's all going. SDSS has a long tradition of honoring its policies and having good policies that support everybody doing science. We have, a commitment to early career scientists and for them to become leaders. I always say, if you love your data, set them free. DR19 is dropping this summer. And I do want to quote Chuck again. One of his graduate students, said, well, Chuck says, just look at the damn thing. I'm like, that's exactly right. That's what you need to do with these spectra. That's what we need to do. And of course, there's, thousands of papers. And when you set the data free, of course, the halo factor is high in terms of the amount of science that can be done. What's happening with those old plates? Well, we're giving them to teachers to teach kids about astronomy. So this is a summer school that Neil Brandt ran at Penn State, where these teachers take home plates and then they actually build curricula for their classrooms. And I think now more than ever, we have to think about that. We also have do some high art. So this is now permanently at the LACMA. So I encourage you all to go see that. This is my advisor, David Weinberg, worked with Josiah McElhaney to make this sculpture, which actually does encode the real clustering of galaxies and quasars in the universe. I think what I like about these types of projects is that it's really a place for builders to learn how to build. You don't know how to do a project like out of the womb, like you have to learn it. Someone has to teach you. It's really a good place to learn those things. Someone today hilariously asked me if I had management classes, which is like a riot because I'm like the opposite of a manager, right? I'm, I explained, well, I had bulldozer classes. But actually, I want to leave you with one final kind of thing. These robotic fiber positioners are changing the game. They're changing the game in terms of the survey speed that we can amass this MOS data. And there may be a Moore's law for galaxy redshift surveys. So here we are, DESI is operating. It looks like DESI 2 is going to run. We've got SphereX, we've got Euclid, we've got Rubin and Roman, and oh my, but as I reflected on this sort of 25 years since Andrew Lang's watershed result, like we are kind of due for a big thing in cosmology. So, we have this picture. This is it's an amazing picture. It's amazing that we've been able to parameterize this model and get it so accurate. But it's still the case that when you talk about dark matter and dark energy, you have to say dark matter and dark energy. Like, we don't know what those things really are at the root reality level that we want to know them at. The DESI results have indicated there might be a crack in that framework, and maybe there's time varying lambda, which is pretty exciting, and that kind of motivates like us to learn more. But of course, we also have Rubin and Roman coming up, and like, what's our strategy for following those things up? So there's a few different ideas. We've got the Spec-S5 program, which is being led by David Schlegel and Arjun Day and Claire Poppett out of Berkeley in Arizona. We've got the MegaMapper concept, which is myself and David Schlegel, and that is, we can multiplex the focal plane. Instead of 500 robots, we can put 25,000 robots. And then you've got the WST project in Europe, which is, again, like, we're talking like not 3 DESI spectrographs, we're talking 30, 40 DESI spectrographs. So it's like massive, massive thing. And at the same time, this ecosystem may be shifting. We might be able to do like faster, better, cheaper space telescopes, which would be fantastic. Maybe we should be thinking not about building another, telescope like this on the ground, but we should be thinking about how to launch these things with Starship. Like, that's going to work, and SLS, and that's going to work. And that's all really, really exciting. And another time I can go into some more detail there. But in the Archway in Blacker House, which was one of the houses that I was a member of as an undergrad, this quote from Ben Franklin: "Dost thou love life? Then do not squander time, for that's the stuff that life is made of." And maybe we ought to think more about the data we have before we, build the next thing. I'm like totally in on building the next thing because I have to have a mission, but actually, maybe we need to think more. Astronomy is phenomenologically so rich, and it's theoretically pretty easy. Like, you got your dynamics, you got your hydrodynamics, you got, you're already in good shape. You got put a little GR in there, and like, you're ready to roll. So it's actually super accessible. So I think we have to think about what the next, thing is. And with that, I think I'm probably out of time. I will take questions. 10x or die, everybody. 10x or die. Yeah, so the decision to go shallow was, thinking we were like, okay, you've got PFS and you've got DESI and you've got Foremost, and like, surely those are going to go so deep. Like, where can we uniquely contribute? And we've got this wide field, and so we wanted to focus on the bright sky. But also, we wanted to get a lot of stars for our galactic genesis program, and that drives those short integration times, because we figured and this was, I take some responsibility for this because I really buy the sort of information theory Kool-Aid of, yeah, like if it's signal to noise of 1 per pixel, like you're integrating too long, right? Which is not true. Like I admit that that's not true, but I would say that design choice, does have a role in certain science cases, but maybe not all the science cases. We are starting to, we're going a little bit faster now than we were, and so now we're exceeding our survey plan, and so we are starting to think, oh, okay, like maybe we should either go deeper or go back. And I always thought, well, we can always go back and stack, and so you lose the time domain aspect, but you get the signal to noise. And so we should just try to cover the sky. But I think that this is a kind of a question that's just like Kareem's binaries. This is a question that's kind of ripe for reevaluation. Like we don't ever want to commit to something if there's a better choice to be made. And so I think there's an opportunity to do that. And I would say that for AS5, which people are starting to think about now, that's a whole different thing. So SDSS burns itself down, at every phase and rebuilds itself. And it does that in order to be responsive to the changing landscape. And so I would say that that's definitely something that people are thinking about for sure in AS5. And there was, you're not the only stellar astrophysicist who is like, the signal to noise spectra is like too low for certain work. For other work, it's really good for training, because now I have n squared stars, like I can do n squared analyses for 6 million stars. And, for like the Milky Way deconstruction part, it's really good. But for other cases, we should think about integrating longer. No matter what you say, no matter what anyone says, in my mind, it turns into a, how can I do better? How can I do better? So it's not your fault, but I think it's good. I think it's a good, well, I wouldn't recommend living that way for anyone else, but I was afflicted. Yes. Yes. Yes, and I should have mentioned that in the talk. So one of the things that we knew that we could do from as soon as we got the robots, in all of the planning phases, we're like, we are going to do time domain spectroscopy, but we can't tell Sri that until the end, because then he'll take over the whole telescope, right? So you got to keep it secret. No, so basically, what we're doing is each of our robots can reconfigure very, very quickly. And so we have a rolling submissions. If you have a time domain, carton that actually needs kind of quick response, and that is like response on, 12 to 24-hour timescales, you can submit cartons, special cartons that are TOO spectra, and those will be observed if they can be observed at high priority. So we don't slew for ambulance chasing, so we don't slew for anything. But if you're in the field and you go off and you're in a TOO carton, we can get a spectrum of you. And so if you have, and Matt and George, I'm sure you guys have tons of programs here. And of course, with ZTF, folks have lots of interesting programs. If you do have a short time domain program, we now have that accepted, and actually those spectra will be, in many cases, if they're interesting to the community, we'll release them as ATELs and that kind of thing. So I think from that perspective, being able to do that time domain and have that, it's a lot of infrastructure. Whenever I say we're doing this thing, it's a huge aircraft carrier to move around. And I have to say, I have to credit Jose Sanchez Gallego and Connor Sayers, who are just, those software engineers that are worth 1,000 person hours. I mean, these people they need to be cloned. They need to be put into some seed bank they make all of this possible. And of course, and we're very grateful. But anyway, this is a real opportunity. And I do want to encourage you guys at Caltech, please, please, please think about this data. I don't want to have like wasted a lot of time having built all this infrastructure and taken all these spectra if like, no one's interested. That would be sad. So make that not true with me. Yes. Oh yeah, so many challenges. So the thing is that in the big shift in SDSS-V compared to SDSS-1 to 4 is that we are really embracing, we're everything but cosmology. So we're really leaning into stellar astrophysics and we're really leaning into accretion, just like messy, phenomenologically rich astrophysics. But the thing is that because they're phenomenologically rich, they're hard. So there are pipelines that have been tuned for like every part of the HR diagram. And so we have a program called Astra, which basically inhales all of the products from each of those pipelines and outputs parameters from them. And you can, depending on if you're looking at young stars like Lynn, or you're looking at, white dwarfs like Kareem, like depending on what you're looking at, or, all the stars like George, you have this meta sort of pipeline. There are a lot of challenges there because you have to synchronize a lot of that pipeline work for our data releases. So right now we have a data release 19 that's like ready. You can do analysis with it. You can do analysis every day. So if you're a black belt astronomer, like you have all the data available to you every day. And that's the data from last night. You don't have to listen, you don't have to use our pipelines, and we release all of that. And the reason we do that is because we are counting on young kids who are going to be like, I can do better than that pipeline. And they're going to do better. And one of those young kids is Andrew Sagery, who was like, I can do better than the Apogee pipeline. And he made an awesome new pipeline called AP Magics, which actually gets really precise radial velocities. So I would say the challenges with pipelines are all the same challenges with pipelines because you're trying to do something uniform, but there's a lot of rich phenomenology and a lot of stuff that happens at the telescope that you have to account for and, take out. And okay, like this lamp was on or this, like all of those things that are happening when you're taking ground-based data are happening in our data. So we have to sort of babysit and watch the pipelines as they go through. And the data releases really do sort of represent, like, we want to be, yeah, you can use this data, it's been vetted. So that's at least the data products, but you can use the raw data at any time. There's tons of challenges there. I think that if you are someone who is interested in software and interested in pipelines, we've got lots of places for you to contribute. But it is certainly, and we have a great data team that's been honed over the years to, they know how to do the data releases, but it's always a stressful thing, and it's always choices that we're making as astronomers about, well, where is this pipeline good? Where should we flag the data? Where is this data not so good? And we're always hoping to improve that and working on improving it. So each field, pardon? The pipeline is, well, okay, so different pipelines. Like AB Magics has data from yesterday. The DRP is a few weeks behind. Well, we want daily tagged reductions of everything. The BOSS pipeline is very well, that's the same, that's basically exactly the same as it's been used in the past. So that has it's not, there's still star targets and all sorts of stuff there that are complicated, but that is easier than the Apogee pipeline because we're doing so many different stars with Apogee. That's the challenging thing there. But I would say we're doing okay. I give us a B-, which I am not happy with. Like, it's not good. Like, we want to do better. I mean, if it was Fiona's class, it would be great to get a B-, but sorry, that's just a shout out to my. I want to put a 6.5-meter telescope in space. I want to fill Starship. Yeah, I want to fill Starship and launch it. But I also want a Ferrari, and I can't afford a Ferrari, Olivier. So this model that Aaron Tohuvalu and others here are working on, and others in the community are working on, about kind of commercial space and faster, better, cheaper, space, that's super enticing, because it's like, if you can do that, like, it just unlocks this whole new thing. You basically use the ground-based telescopes for innovation and development of technologies, and then you launch stuff, and then everyone gets their own 1-meter telescope, right? But like, there's something about that just seems like, okay, well, where's the genie that's granting all these wishes? Like, it seems like it might violate some economic limits and constraints, and so there's nervousness about, I think, about like leaning so hard into that model at the scale of the 6.5 meters, because there's a reason that NASA works the way it does, and like stuff works. Like when SphereX is launched, like it worked, right? And so yeah, so that is a really good example of, you're using the rocket technology developed commercially, but you're actually still kind of in the sort of academic mode. I think this idea that you might do academic mode space projects like the same dirty, messy way we do SDSS and Catalina and ZTF and all of those kind of ways that students can come in and like mess around and mess up. I think that's really exciting, and I'm in for that. But I think, like I said, we live in turbulent times, and you have to be ready for different things. And all I know is that I'm trying to get as many spectrums as possible to think about in the near term. And I think with the infrastructure that we have now, I do feel like we have a lot to think about, and we have a lot to look at. And I think that also wouldn't be terrible, right? But I as I'll talk about in my lecture tomorrow, to those of you who come, we have to think ambitiously about what science of the future looks like, and what that might look like with great upheavals. And surely there will be some steady state things. I think places like Caltech, or like sort of strongholds of in this turmoil. But there's a lot of other places that won't be able to just kind of stay the course. And what can be done in that context? What can be done with, there's a lot of smart people who are excited about doing this kind of science. And what does it mean about, you learn a lot of different things building an instrument for a telescope. I mean, you could teach a lot of stuff if the only thing, Plato said that you had to, well, really Socrates through Plato said that you had to learn geometry first and then astronomy. I mean, he didn't have these telescopes, so I don't know. But I think you can learn a ton about math, physics, chemistry. You could have a whole university curriculum just through SDSS, just through astronomy, electronics engineering, software engineering, data science, and so on the one hand, we're sort of in the attic of the ivory tower, and on the other hand, we're in the basement, and we can actually build things up from the bottom. And that, being Caltech, and forgiving Hale for being so excited that like all the women weren't let in anymore, which is like really sketchy of him. Anyway, but being here where they actually built something out of like an orange field, we should think ambitiously.